America's refineries are running at 96% capacity. There is very little buffer left. One major disruption, and the system has nowhere to go. The suspect is not the oil field, it's the infrastructure between the well and the pump. A system built to move millions of barrels every day, with almost no tolerance for interruption. Count 1. When Hurricane Katrina hit in 2005, fuel shortages appeared within 72 hours. Count 2. That was one region. A national disruption puts pressure on the entire system at once. Count 3. At 96% utilization, there is little spare refining capacity to absorb a major disruption. Something in this system fails first, and it isn't where most people are looking. In this case, we follow the oil from the well to the pump and identify the first pressure point before the shortage ever reaches your gas station. Case file open. The U.S. pumps 13.2 million barrels of crude every day, an all-time production record. The ground isn't dry. West Texas isn't out of oil. That's what makes the failure dangerous. The trap isn't under the dirt. America has plenty of oil. The problem is, your car is annoyingly specific about what counts as fuel. Crude coming out of the ground doesn't go straight into your fuel tank. It has to be processed into gasoline, diesel, jet fuel, and the other products the economy actually uses. And every barrel leaving places like the Permian Basin has to move through a network of gathering systems, pipelines, storage hubs, and terminals before it reaches a refinery. That network depends on one thing: movement. Take Cushing, Oklahoma, one of America's major crude storage and trading hubs. Its tanks provide a buffer between incoming and outgoing flows, but they aren't bottomless. If a major pipeline stops moving crude for 48 hours while production upstream continues, the problem doesn't disappear. The oil starts backing up, storage fills. And once there is nowhere left to put incoming crude, producers upstream have one option: pull back production. The initial breakdown doesn't begin because America suddenly has no oil. It begins when the pathway carrying that oil toward the refinery loses the capacity to keep moving it. The shortage doesn't start at the pump. It starts here, before the oil ever reaches the refinery. And the refinery is the next problem, because the system built to turn those barrels into fuel is already running close to its limit. A refinery is not a giant microwave. You don't turn the dial to 110% when America suddenly needs more fuel. Running this network near its maximum capacity isn't a sign of efficiency. It's a structural trap. A refinery is a massive, continuous chemical process operating under extreme heat and pressure. When you push steel to its mechanical threshold, the margin for error gets very small. If a single fluid catalytic cracking unit trips at a major Gulf Coast facility, like Motiva in Port Arthur, you don't simply lose one piece of equipment. You lose a chunk of refining capacity from a system that has very little room left to absorb the loss. And here is the physical constraint most people miss. There is no large reserve of refining capacity sitting idle, waiting to be switched on. Most of the available capacity is already being used. Expanding processing capacity takes years of heavy engineering, regulatory approvals, and billions in capital investment. When domestic fuel demand spikes or a major pipeline trips, that remaining operational buffer can disappear quickly. The wall is visible. What's building behind it isn't. Because while refineries are operating near their limits, three entirely different industries are about to compete for the exact same gallon. A barrel of crude doesn't produce just one product. Refining it yields gasoline, diesel, jet fuel, and when output is constrained, every industry that depends on those products is suddenly competing for the same limited supply. They don't all get an equal share. And refineries have limited flexibility in how much of each product they produce. So when total fuel supply tightens, the competition isn't theoretical. First, logistics. Heavy trucks move roughly 70% of domestic freight by weight. Most of them run on diesel. Second, aviation. U.S. commercial aviation consumes roughly 1.5 million barrels of jet fuel every day. There is no electric shortcut waiting on the runway. Third, agriculture. During planting and harvest seasons, farm equipment depends heavily on diesel. A fuel shortage arriving in April or September doesn't wait for the harvest. And passenger vehicles, running on gasoline, are competing inside the same constrained system. Prices rise, contracts get enforced, inventories determine who stays supplied and who feels the shortage first. The market doesn't divide the shortage equally. It has its own logic for deciding who gets served and who gets exposed. That logic is the next thing to examine. A large portion of America's fuel supply is already spoken for before a shortage begins. Not rationed, not allocated by government order. Committed through long-term supply contracts signed months or years in advance. Major freight carriers, airlines, utilities, and other large industrial buyers often secure fuel through these agreements. They enter a shortage with contractual rights to supply that many other buyers don't have. Buyers without those contracts, including many fuel terminals that supply retail gas stations, compete for whatever volume is available on the open market. That distinction is invisible in normal conditions. When supply tightens, it starts determining who stays supplied and who feels the pressure first. And when refinery output drops, or a pipeline allocation falls, inventories, existing commitments, logistics, and market prices start determining the outcome. Not simply need, not urgency, not proximity to the refinery. Retail gas stations sit at the visible end of this chain. They depend on wholesalers, terminals, pipelines, inventories, and the broader regional fuel market to keep their pumps supplied. So the driver watching a price jump at the pump isn't seeing the beginning of the shortage. They're seeing the end of a chain reaction that started much earlier. The consumer isn't necessarily first in line. They are where the shortage becomes visible. And once the pressure reaches the retail market, the next problem is geography, because a fuel shortage in Texas doesn't behave the same way as a fuel shortage in New York. Shortages don't hit America evenly because the country isn't one connected pool of fuel. It moves through refineries, pipelines, storage terminals, waterways, rail, and trucks. Every link has limits. First, refinery locations. Over half of domestic refining sits along the Gulf Coast. When a major facility trips, distant regions have limited options for replacement fuel. Second, pipelines. Millions of barrels move through systems like Colonial and Plantation. You don't reroute millions of gallons overnight when a primary corridor goes down. Third, storage. The Northeast has minimal local refining capacity. It depends heavily on Gulf Coast pipelines and marine imports. Disrupt either, and its buffer evaporates. Fourth, transportation. Moving replacement fuel by water, rail, or truck takes time and spare capacity, neither of which exists during a national disruption. So the same shock produces different outcomes. One region sees higher prices, another burns through inventory. A vulnerable region runs out of options. The map determines who absorbs the blow. When that region reaches its limit, the failure surfaces, at the terminal, at the pump, in the price. And that moment of visibility is the next thing this case needs to examine. Before the public notices a single penny at the pump, the market has already started reacting. The first crack appears upstream, at the wholesale rack. Terminal operators watch fuel prices move as buyers compete for limited supply. Crude prices don't have to surge first. The price of finished fuel can move sharply when the market starts pricing in tighter availability. Then the physical squeeze reaches distribution. Tank trucks arrive at regional terminals looking for fuel. The Colonial Pipeline disruption in 2016 showed this mechanism in real time. When that pipeline went down, fuel supplies across the Southeast tightened. Gas stations in multiple states reported shortages within days, not weeks. And when a major supplier declares force majeure, contractual deliveries can be disrupted across the chain. By the time a gas station changes the numbers on its sign, the pressure has already moved through the wholesale market, terminal, and transportation network. The system didn't suddenly run out of fuel. The delivery network reached its limit first. The consumer was simply the last part of the chain to see it. But the price at the pump isn't where the chain reaction ends. It's where it starts becoming everyone else's problem. When the price at the pump surges, most drivers see a hit to their personal budget. The larger damage happens out of sight, inside the systems moving everything else. Gasoline moves commuters. Diesel and jet fuel move the economy. Diesel prices rise. Freight operators pay more to move goods. Those costs move into the price of everything being shipped, quickly. Farm equipment depends heavily on diesel. And fertilizer, which depends on natural gas as a feedstock, adds a second energy cost into the food supply chain. A fuel squeeze raises the cost of getting food from the field to the market. Airlines pay more for jet fuel. Fares adjust. Routes get evaluated. The aviation network absorbs what it can and passes the rest forward. Factories pay more to move raw materials and ship finished products. Energy-intensive operations pay more to run. Each sector absorbs the cost and passes what it can't absorb forward. The fuel shortage doesn't stay inside the fuel market. It moves through transportation, food, aviation, and manufacturing, and eventually into household prices. What started as a supply problem at a refinery is now a cost problem in every sector that depends on movement. And movement is how everything reaches the consumer, which means the last person to feel this is absorbing the compounded cost of every link that came before them. The driver pays at the pump, the shopper pays at the checkout, and neither sees the refinery where the chain began. At the end of this physical chain sits the individual. By the time the shortage reaches the neighborhood gas station, the system has already run out of easy options. You feel it first in the daily routine. The commute costs more. The delivery fee goes up. The flight for a family visit gets repriced. Then it reaches the household budget. The grocery bill reflects the diesel used to move food across the country. The price of manufactured goods reflects the fuel required to move raw materials and finished products. You don't get a notification when a pipeline loses capacity in Texas. You don't see the contracts, inventories, terminals, and transportation decisions working behind the scenes. You simply see the result. Less margin in your paycheck, higher prices on the shelf, a commute, a delivery, a flight, all quietly repriced. The system has passed the cost of its physical limits all the way down the chain, from the wellhead to the wallet. So when does an energy shortage become your problem? The moment you buy anything that had to be moved. And now the chain is complete. Which leaves one question: why does it keep breaking the same way? Because the system has the same weakness every time. It depends on continuous movement. Oil has to leave the well, travel through pipelines, reach refineries, and move back through the distribution network. When one link loses capacity, the pressure moves downstream. Storage fills. Inventories fall. Prices rise. And eventually, the consumer sees it. America doesn't need to run out of oil for an energy crisis to begin. It only needs the system to lose its ability to move what it already has. The oil can still be underground. The crisis has already started. Case closed.